Hello everyone and welcome to our calculus notes on section 4.3. Today we're talking about Riemann sums and definite integrals. So first let's deal with Riemann sums. So consider the sum whose limit is defined to be the area of the region under the graph of f of x. And this is a continuous non-negative function, just like we've been dealing with, between x equals a and x equals b. So here we have the sum of I equals 1 to n of f of c sub I times delta x. And this is where delta x is b minus a over n, and it's going to be the same for every subinterval. Now, if we generalize this sum to allow for varying widths in each subinterval, we have the definition of a Riemann sum. So far we've developed this, and we talk about how this applies to area under a curve. And all a Riemann sum does is take this delta x and make it variable, meaning the width can change in between the subintervals. So it says let f be defined on the closed interval a to b, and let delta be a partition of the interval a to b, given by a equals x sub 0 is less than x sub 1 is less than x sub 2, so on and so forth, all the way up to x sub n, and then that's got to be b, where delta x sub I is the width of the ith subinterval. So if c sub I is any point in the ith subinterval, then the sum from I equals 1 to n of f of c sub I delta x sub I, and you can see c sub I has to be between x sub I and x sub I minus 1, meaning it has to be on that subinterval, is called a Riemann sum for the partition delta. Okay, so all of that stuff really just means we're going to take these delta x's and we're going to make them of any width. And you can see that all of our x values here to make our subintervals just have to be in order. Okay, they don't have to be spaced evenly apart. And here's what that looks like. So you can see here from A to B, and we can see a couple partitions. Here's x sub 1, here's x sub 2, and you can notice that c sub I actually falls somewhere in this interval. And so you can see the height of this rectangle here is somewhere in between that, the two subintervals here, in that partition. So consider the region bounded by the graph square root of x and the x-axis on the interval 0 to 1. Okay, so I'm going to draw our interval. Okay, and here's our square root of x. Here's the x-axis. It says evaluate the limit where c sub I is the right endpoint of each partition given by c sub I equals I squared over n squared, and delta x sub I is the width of the ith subinterval. So here you have the definition of the Riemann sum. Okay, and now we want to partition this up here. So our first partition is just going to fall right here. And if it's your first partition, you're going to let I equal 1. So if I equals 1, then our first partition is going to be 1 squared over n squared. Because that's all that I means. It's which partition is it. Okay? Now our next one then, when I equals 2, the partition is going to be 2 squared over n squared. Okay? For our third partition, here I equals 3. So here we're going to get 3 squared over n squared. And this really continues on and on until we get to, okay, so that just continues on and on until I equals n minus 1. Okay, so this would be n minus 1 squared over n squared. And then here it would go all the way up to n squared over n squared because I equals n here at the end of our interval, 0 to 1. Okay, so don't worry too much about how we found this out. Just realize that this is how it's going to be partitioned. Now, if we look at this, and we want to find our sum here. Let's go ahead and draw our rectangles. So we draw each of these partitions, and let's go ahead and use upper sums. Okay, so we want it just above our curve. Okay, and let's go ahead and figure out what these y values would be here. So if we have I squared over n squared, and remember our function f of x equals the square root of x, okay, basically means y is going to equal the square root of x. So if we took the square root of 1 squared over n squared, we would just have 1 over n. This next one, square root of 2 squared over n squared, that's just going to be 2 over n. Okay, so on and so forth. Okay, the second to last one here is going to be n minus 1 over n for your height. And then the last one will just be n squared over n squared, so the square root of that is just 1. Okay. So what we want to do first is find delta x sub I. Okay, and that's going to be the width of any of these partitions. So because c sub I is given by this equation I squared over n squared, what we're going to do is start off with the I squared over n squared. So that is the x value of any partition. And if we want the width, we need to subtract the value of the partition, the x value of the partition just previous to this. So the one before I is going to be I minus 1. Okay, so this could be like this partition if I was 3, and then this would be the other partition if I was 2. And we can see that that works out there. Now let's go ahead and simplify this down so that we can get a better looking formula here for delta x sub I. Okay, so it's going to be I squared over n squared minus, let's go ahead and square I minus 1. Well, that becomes I squared minus 2I plus 1 over n squared. And now we can combine these. And so delta x sub I, let's see, I squared minus I squared is gone, minus negative 2I, so that's positive 2I, and then minus positive 1 is minus 1 over n squared. So now we have our delta x sub I. So let's go ahead and plug this all into our Riemann sum here. And as we write this, the limit as n goes to infinity. Let's think about what that means. If n goes to infinity, that means we're going to be increasing the number of partitions still to infinity. All right, and so here we have the sum I equals 1 to n, and then f, well, our function is the square root, and it's of c sub I, and c sub I is I squared over n squared. Okay, and then this is times delta x sub I, so that's 2i minus 1 over n squared. Okay, so let's go ahead and find this limit. This is your Riemann sum here. And we can do a little simplifying here. The square root of I squared over n squared is just I over n. And this is going to be times 2i minus 1 over n squared. And we still have the sum. So we don't want to lose that notation. The limit as n goes to infinity. Okay, and let's go ahead and multiply here. Now rewrite our limit. Okay, so that's going to give us 2i squared minus I over n cubed. Okay, now let's go ahead and figure out this sum here. And we're going to do that of course, by splitting these two up here. So we'll have the limit as n goes to infinity. So we'll have 2i squared over n cubed, and then minus I over n cubed. Okay, so here this is going to be the limit as n goes to infinity, and I squared changes into 2n cubed plus 3n squared plus n over 6, and we're going to keep that 2 over n cubed here, multiplying. And then here, I changes into n squared plus n over 2, and we're going to keep the 1 over n cubed here. And that's multiplying. Now we can just apply the limit as n goes to infinity. Here the exponents are the same. So this is 2 times 2 over 6, which is 2/3. And then here, it's bigger on the bottom, so this is 0, so minus 0. So our final answer is 2/3. So what we found here is that the area under this curve is 2/3. All right, so this was our first example where our partitions did not happen on equal subintervals. And so we're going to change this again to say the width of the largest subinterval of a partition delta is called the norm of the partition, and we're going to designate it with this symbol right here. Okay, so it's kind of like a double absolute value of our delta. That's what it looks like, but it's the norm of the partition, which is the largest subinterval. Now a partition where every subinterval is of equal width, so basically where all your delta x's are the same, b minus a over n, we call this a regular partition. And that's what we were dealing with earlier until we got to the Riemann sum where our partitions were different widths. Now for a general partition, the norm is related to the number of subintervals like this. So b minus a over your norm is going to be less than or equal to n, okay, because this is your greatest subinterval. So what this brings us to is finally, our definite integrals. So it's been a long journey, and this is where all the hard work with our sums and everything is going to pay off big time.